At the end of this video, you should be able to identify different types of collisions, determine the changes in kinetic energy during perfectly inelastic collisions, compare conservation of momentum and conservation of kinetic energy in perfectly inelastic and elastic collisions, and find the final velocity of an object in perfectly inelastic and elastic collisions. Chapter 6, Section 3, Elastic and Inelastic Collisions. As you go about your day-to-day activities, you probably witness many collisions without really thinking about them. In some collisions, two objects collide and stick together so that they travel together after the impact. An example of this action is a collision between football players during a tackle, as is shown on the screen here. In an isolated system, the two football players would both move together after the collision with a momentum equal to the sum of their momenta, plural of momentum, before the collision. In other collisions, such as a collision between a tennis racket and a tennis ball, two objects collide and bounce so that they move away with two different velocities. The total momentum remains constant in any type of collision. However, the total kinetic energy is generally not conserved in a collision, because some kinetic energy is converted to internal energy when the object deforms. In this section, we will examine different types of collisions and determine whether kinetic energy is conserved in each type. We will primarily explore two extreme types of collisions: perfectly inelastic collisions and elastic collisions. Perfectly inelastic collisions can be analyzed in terms of momentum. When two objects, such as the two football players, collide and move together as one mass, the collision is called perfectly inelastic collisions. Likewise, if a meteorite collides head-on with Earth, it becomes buried in Earth, and the collision is perfectly inelastic. Perfectly inelastic collisions are easy to analyze in terms of momentum, because the objects become essentially one object after the collision. The final mass is equal to the combined masses of the colliding objects. The combination moves with a predictable velocity after the collision. Consider two cars of masses m1 and m2 moving with initial velocities v1 initial and v2 initial along a straight line, as is shown on the screen here. The two cars stick together and move with some common velocity vf along that same line of motion after the collision. The total momentum of the two cars before the collision is equal to the total momentum of the two cars after the collision. This simplified version of the equation for conservation of momentum is useful in analyzing perfectly inelastic collisions. When using this equation, it is important to pay attention to signs that indicate direction. In the figure on the screen here, V1 initial has a positive value, meaning M1 is moving to the right, while V2 initial has a negative value, meaning M2 moving to the left. At this point, you should be able to understand sample problem E. Kinetic energy is not conserved in inelastic collisions. In an inelastic collision, the total kinetic energy does not remain constant when the objects collide. Some of the kinetic energy is converted to sound energy and internal energy as the objects deform during the collision. This phenomenon helps make sense of the special use of the words elastic and inelastic in physics. We normally think of elastic as referring to something that always returns to or keeps its original shape. In physics, an elastic material is one in which the work done to deform the material during a collision is equal to the work the material does to return to its original shape. During a collision, some of the work done on an inelastic material is converted to other forms of energy, such as heat and sound. The decrease in the total kinetic energy during an inelastic collision can be calculated by using the formula for kinetic energy. It is important to remember that not all of the initial kinetic energy is necessarily lost in a perfectly inelastic collision. At this point, you should be able to understand sample problem F.
Collisions of all types occur around us all the time. One common type of collision is an inelastic collision, where two objects stick together and move onward as one object. In these collisions, the final mass of the object is the sum of the masses before the collisions. If one of the objects is stationary, the equation is easily solved. Even if both objects are moving, the equation is still fairly easy to solve because the final mass is equal to the sum of the original masses and there is only one final velocity.
Elastic collisions. When a player kicks a soccer ball, the collision between the ball and the player's foot is much closer to elastic than the collisions that we have studied so far. In this case, elastic means that the ball and the player's foot remain separate after the collision. In an elastic collision, two objects collide and return to their original shapes with no loss of total kinetic energy. After the collision, the two objects move separately. In an elastic collision, both the total momentum and the total kinetic energy are conserved. Most collisions are neither elastic nor perfectly inelastic. In the everyday world, most collisions are not perfectly inelastic. Colliding objects do not usually stick together and continue to move as one object. Most collisions are not elastic either. Even nearly elastic collisions, such as those between billiard balls, result in some decrease in kinetic energy. For example, a football deforms when it is kicked. During this deformation, some of the kinetic energy is converted to internal elastic potential energy. In most collisions, some kinetic energy is also converted into sound, such as the click of a billiard ball colliding. In fact, any collision that produces sound is not elastic. The sound signifies a decrease in kinetic energy. Elastic and perfectly inelastic collisions are limiting cases. Most collisions actually fall into a category between these two extremes. In this third category of collisions, called inelastic collisions, the colliding objects bounce and move separately after the collision, but the total kinetic energy decreases in the collision. For the problems in this course, we will consider all collisions in which the objects do not stick together to be elastic collisions. Therefore, we will assume that the total momentum and total kinetic energy will stay the same before and after a collision in all collisions that are not perfectly inelastic. Kinetic energy is conserved in elastic collisions. The image on the screen here shows an elastic head-on collision between two soccer balls of equal mass. Assume, as in earlier examples, that the balls are isolated on a frictionless surface and they do not rotate. The first ball is moving to the right when it collides with the second ball, which is moving to the left. When considered as a whole, the entire system has momentum to the left. After the elastic collision, the first ball moves to the left and the second ball moves to the right. The magnitude of the momentum of the first ball, which is now moving to the left, is greater than the magnitude of the momentum of the second ball, which is now moving to the right. The entire system still has momentum to the left, just as before the collision. Remember that V is positive if an object moves to the right and negative if it moves to the left. At this point, you should be able to understand sample problem G. The total momentum is always constant throughout the collision. In addition, if the collision is perfectly elastic, the value of the total kinetic energy after the collision is equal to the value before the collision.
During an inelastic collision, the objects deform and they move separately after the collision. The total kinetic energy decreases. During a perfectly inelastic collision, the two objects stick together and their final velocity is the same. The total kinetic energy decreases. During an elastic collision, The objects bounce apart and move separately. There is no change in the total kinetic energy.
At this point, you should be able to identify different types of collisions, determine the changes in kinetic energy during perfectly inelastic collisions, compare conservation of momentum and conservation of kinetic energy in perfectly inelastic and elastic collisions, and find the final velocity of an object in perfectly inelastic and elastic collisions.